Okay, so it gives me great pleasure to introduce Euan McLeod. Euan is an assistant professor in the College of Optical Sciences at the University of Arizona since 2015. He's also an assistant professor of the University of Arizona Bio 5 Institute and an affiliate member of the University of Arizona Cancer Center. He was previously a postdoc in electrical engineering and bioengineering at UCLA, as well as a postdoc in applied physics at Caltech. He received his PhD in mechanical and aerospace engineering from Princeton University and his BS in mechanical engineering with honors from Caltech. Euan is a senior member of the Optical Society of America and a life member of SPIE. Euan's background and interests lie at the intersection of optics, nanoscience, and soft biomaterial science. He has published more than 35 papers on these topics in peer-reviewed journals, with major contributions in the areas of high-speed variofocal lenses based on acoustic modulation, lens-free holographic imaging of nanoparticles, viruses, and biomarkers, and the use of optical tweezers in fabricating micro and nanostructured materials. His PhD work on tunable acoustic gradient index tag lenses led to numerous innovation awards, including a 2013 R&D 100 Award, a 2013 SPIE in Photonics Media Prism Award, and a 2017 Thomas Alva Edison Patent Award. This patented technology is now fully licensed by Mitutoyo Corp and commercially sold. So whenever you're ready. You're muted too.
There we go. Okay. Thank you. Let me go back. Okay, yes, thank you for the introduction. So today I'm going to talk about our work in soft material nanophotonic systems. So our group works at the intersection of kind of these two areas. So nanophotonics is the study of how light interacts with particles or features that are smaller than the wavelength of light. And then soft materials are things like colloids or liquids or polymers or biological materials. And so we're interested in kind of the intersection of those two areas. So go back to the laser pointer here. So I'd like to start off with some acknowledgements here. Of course, all the work is done by the students in my group, and I have the honor of presenting it. Andy and Jeffrey recently defended their PhDs. Andy's now working at Apple, and Jeffrey's a postdoc here still at the University of Arizona. And then Waylon, Miriam, and Colin are graduate students, are PhD students in my group. And then Lei and Hui were visiting scholars here for a while, and Florian was a master's student. And so we've gotten some support also from the high performance computing services at U of A, and we've been lucky enough to get financial support from NSF and DITRA and the University of Arizona. So what I'm going to talk to you today, I'm going to divide into three areas. The first is going to be on optical positioning and linking, which we've called OPAL. And this is essentially a fabrication approach, a 3D fabrication approach. So I'll start out talking about some existing micro nano fabrication techniques, and then show how we can assemble 3D structures from hundreds of microscale building blocks. I'll discuss positioning accuracy and the building block manipulation speed, and then some things that we've discovered regarding the modeling of trapping forces on nanoparticles. And then the second part, I'll talk about device design and applications of OPAL. And one of those cases is augmented microtoroid optical resonators, which is a collaboration with Judith Su's group. And then we're also using nanoshells for creating light guiding structures. And I'll discuss a little bit about some simulation work that we do with a coupled dipole method for structure design. And then at the end of the talk, I'll discuss some work that we have recently done on creating biosensors using lens-free holographic microscopes. And this we call our QLab sensor. And it relies on some improved reconstruction algorithms for small targets in holographic microscopy. And we've used it to do specific protein sensing. So I'll discuss that as well. So some common, if you think about micro nanofabrication, especially in the area of photonics, what people probably first think of is photolithography. So that's the most common 2D micro nanofabrication method. It's very widely used, for example, for integrated circuit fabrication. It's done in a clean room. The idea is you have some sort of photoresist, and then you expose part of that photoresist using a mask that's only going to let you expose part of it. And then depending on the type of photoresist, the exposed part either gets etched away or the exposed part gets protected and the rest gets etched away. And this is how you can fabricate 2D structures. So it's kind of difficult to do this to advance for 3D fabrication because you'd have to do many, many layers one after the other, and you have to register each layer. So people do this, but it becomes more and more challenging the more three-dimensional your structure is. Electron beam lithography is similar in a lot of ways. The only main difference is that rather than having light be the exposing radiation is really these electron beams. And so you would do the same sort of process, but in an electron microscope. It gives you a higher resolution, but it's still really a 2D process. And then another common 2D process is nano imprint lithography, which is kind of like stamping or molding a big big area, so it's useful for cost-effective replication. But none of these approaches can be easily extended to 3D fabrication. So 3D fabrication often utilizes additive processes. So whereas what I showed you on the previous slide, we're taking away photoresist by developing it, in this case, we're typically adding structures. One example is laser-induced forward transfer, where you have some material on a donor substrate that you then transfer to a receiver substrate using a pulsed laser beam, and people can build 3D structures using that sort of approach. Another common approach is self-assembly. So this is a lot of times just based on chemistry, and I've done some work on that in the past. So if you saw my talk maybe 5 years ago at the Colloquium, I talked a lot about how we were building these self-assembled nano lenses for sensing using Lensfree holographic microscopy. And then another very common 3D fabrication approach is two-photon polymerization. So in two-photon polymerization, a laser beam is focused into a photocurable resin. So the idea is that there's some sort of glue that will cure and harden when exposed to a certain wavelength of light. That's usually in the blue or ultraviolet range. And the idea is you use a laser beam that has a wavelength that's twice that value, so that when two of those photons kind of reach the same spot at the same time, they cause that, that curing effect. And so then you can scan your laser beam through your sample. And as you scan the laser beam through the sample, you can harden certain areas of the resin. And then when you're done, you wash all the rest of the kind of viscous liquid resin away. So this has achieved a lot of success. It's been commercialized by the company Nanoscribe. And I'm going to zoom in here on this too here. It's very good at creating sort of complex 3D structures. You can get resolution that's maybe about 160 nanometers laterally and maybe about 400 nanometers vertically. But there are a few issues with it that we'd like to solve. One that you can kind of see from this picture is there's a little bit of shrinkage. So the idea is when this gets developed, the whole structure, as the solvent is washed away and evaporated, the structure itself shrinks a bit. But if it's been constrained by adhesion to the substrate, basically this bottom layer here can't shrink, and then these upper layers shrink. And so you see that there's a little bit of a curvature kind of right here, and that's due to shrinkage. And so that's one of the downsides of these, this sort of technique. So other challenges with these existing approaches are achieving very small resolution, so achieving resolution better than 100 nanometers. This plot on the right here shows a variety of different papers from different techniques. So in the laser-induced transfer, the direct ink writing, electrohydrodynamic printing, optical tweezers, which is what we're going to talk about a lot in this talk, and then the two-photon polymerization. And so you can see that if we're trying to get 100 nanometer feature sizes, that's basically this area on the far left, it's pretty rare and it's pretty difficult to get feature sizes smaller than that. It's also can be challenging depending on the technique to get complex 3D geometries. So the two-photon polymerization is pretty good at getting that, but for other techniques, if you want to print like overhangs or bridges or these sorts of things, that can be challenging. Another challenge is heterogeneous material integration. So a lot of exciting devices and materials aren't built out of just a single material, but you want to mix things like dielectrics and metals or maybe semiconductors together in some sort of pattern. And so how can you do that is often a challenge. Shrinkage I mentioned on the previous slide. Another challenge is augmenting and repairing existing structures. So if you have some large microstructure that you want to decorate with nanoscale features, how can you do that? And then a final challenge is changing feature size on the fly. So a lot of times if you're fabricating devices, there might be large areas that you just want to fill up with a lot of material very quickly. And then there are other areas where you want a lot of very fine detail. And so it'd be helpful to have large features and small features, being able to switch back and forth on the fly. And so in our group, we're developing an optical tweezer platform called Optical Positioning and Linking, OPAL, to overcome these challenges. So these are some examples of 3D devices that could benefit from OPAL. This is a simulation of what could be considered either a super resolution imager or a high density photonic interconnect. In this case, we're kind of simulating it as an imager. The idea is we have light sources here, and these light sources are kind of positioned in this numeral 7 pattern. And away from each of these light sources, we've built a chain of particles. It's going to act like a transmission line or a waveguide, kind of. Not exactly a waveguide, but a little bit like a waveguide. And so the idea is these light sources by themselves are so close together that they're beyond the diffraction limit. And so they would just look like a single spot. But then if we build this structure, what we can do is we can relay that light up to a plane where we get the light is separated much farther than the diffraction limit, and then we can use free space optics to image that. So you could think of this as a magnifying imaging device for super resolution imaging. If you ran it in the backwards direction, you'd be able to take light and then focus it down to a lot of spots here. And you could imagine these might be ways of launching light into some sort of photonic integrated circuit. And so this would be a way of doing that 3D connection from one photonic integrated chip to another photonic integrated chip. Other examples are things like photonic metamaterials. So this is ways of patterning materials at sub-wavelength length scales to get negative refractive index, or epsilon near 0. This is an example of a simulation of a negative index material. You have light that's coming in from the top here, and then when it hits the surface, some of it is going to get reflected, but some of it is going to get transmitted through this structure. And let's see if I can disable the laser pointer. Go back and play that again. So we'll play it again. So what you can see is you can see that within this negative index material, the phase velocity of the light is actually going in the opposite direction of the pointing vector of the light. So the pointing vector of the light is still generally going downwards and to the right, but here the phase velocity is going backwards, and so that's an illustration of this negative index material. If you have very good control over the index from different types of unit cells, and you start to build up this kind of continuously spatially varying index in a material, you can start to build devices based on transformation optics, which is a way of designing devices to kind of guide light through systems. Probably the most famous example of this is optical cloaks, but there are other sort of devices that you can build with that too. We have a grant where we're trying to use this approach to build multifunctional image sensor pixels. And so the idea is we can position building blocks in 3 dimensions above an image sensor pixel in order to make it sensitive to a particular incidence angle. So the idea is this image sensor pixel would pick up one particular angle of light coming in. And then I'm going to talk a lot about this later in the talk, is augmenting these microtoroid optical resonators to build more sensitive and robust biosensors. So those are just a few examples. So I'm going to move now into how our approach works and some kind of performance characteristics of it before I go back and talk more about a couple of those applications in detail. So our approach is based on using optical tweezers to grab individual particles and move them around and then position them. So optical tweezers were invented by Arthur Ashkin in 1970, and he only recently won the Nobel Prize for this in physics in 2018. And the main idea is momentum conservation. So photons carry momentum, and that's given by Planck's constant over the wavelength. And so you could imagine, let's say you have some microscopic particle that's maybe like a transparent bead, a polystyrene bead or a silica bead or something like that. It's near a laser beam. The optical axis of the laser beam is going in the z direction. And because the beam is more or less Gaussian, you could imagine that the brightest part of the beam is on the optical axis, and then the beam intensity kind of fades away as you move off the optical axis. So you can imagine that this is a plane wave. So these rays are coming in, they're hitting the sphere, they're going to get refracted, and they get bent down. So because these light rays have changed direction, that means the momentum of the photons have changed. And if there's a change in momentum, there has to be a force exerted on something by Newton's laws. And so that force is going to be stronger from the rays coming from the brighter part of the beam than it will be from the rays from the not so intense part of the beam. And so you're going to end up with net forces that pull you towards high intensity optical regions. And then there are also forces that tend to push you downstream, these radiation pressure forces. And if you combine this with a very high numerical aperture microscope objective, you can get a situation where the gradient forces dominate, and your particle is going to be trapped at the focus of that laser beam. Basically, the particle is going to be attracted to that high intensity region. So a lot of people before us have also used optical tweezers for assembling structures, and so there are a few examples on this slide. For the most part, these structures have been from microscale building blocks. They're 2, 3, 5 microns in size. This is the smallest previous one we found, where they assembled particles that were a little bit less than 1 micron out of silica. And our main goals over these previous studies is to increase the system scale, so to try to work with more building blocks to build more complicated structures, reduce the building block size so that we can work with smaller materials, because a lot of the interesting applications we can only really achieve if our building blocks are sub-wavelength, and then also extend the range of materials. So rather than working with just polystyrene beads or silica beads, we can work with metals or semiconductors or these sorts of things. So this is a schematic of our approach. We have a fiber laser that we then couple into free space, and this is going to come down through our microscope objective, and we're going to form our optical trap at the focus of this microscope objective. We have a microfluidic sample chamber on a computer-controlled translation stage. And then we have a white light source for imaging the beam and imaging, basically not the beam, but imaging the sample and everything that's happening. Our general operation is we acquire a particle that we want to trap. And typically we're going to acquire those particles from these inlets. So the idea is we're going to flow particles into our microfluidic device from these inlets. We're going to grab one. We're then going to bring it to the region where we want to build something, and then we're going to place the particle. And there are a lot of kind of recalibration steps to make sure that we try to get the best accuracy we can in doing this. This is another example of a photo of how this looks in our lab, but it's a similar, kind of similar to what I showed on the previous slide. So this is an example of a LabVIEW base. So this was LabVIEW interface. This was built by Jeffrey Melzer, and it's basically integrating all the different components of our system so we can control our camera, our laser, our translation stage. We have a quadrant photodiode that we're working on integrating with our system too. So this would be a map of our microfluidic device. So this is a particle that we've grabbed in our optical trap, and we're now dragging the chip underneath the particle, basically so that we can position the particle where we want to here. And you can see that there are a few other particles that have been positioned previously, and so we can then bring this down and attach it where we want to attach it. And so this can be fully automated in the idea that we can just program all the coordinates of where we want to put the particles, and then we can grab the particles. So once the particle gets positioned where we want it, how do we get them to stick and stay in place? The approach we use is this biotin-avidin binding. So biotin and avidin are two biological molecules that bind very strongly together. Basically, their binding interaction is almost as strong as a covalent bond, but it's not quite covalent. And the advantage of this is that particles of the same type do not bind to each other. So biotin doesn't bind to biotin and avidin doesn't bind to avidin, but they bind to each other. So if we're working with these particles, once we position one next to the other, that binding is then permanent and those particles stay in place. So a lot of cases, we can buy these particles directly with these types of coatings commercially. In other cases, we have to do a little bit of chemistry ourselves. Pretty much all commercial suppliers of micro and nanoparticles will provide a carboxylic acid surface coating on their particles. And then we can use this EDC NHS chemistry to attach any type of amines to these groups. And so these avidin molecules are proteins. Basically, any protein will have a free amine group on the end that we can attach. And in the case of biotin, we can buy specific molecules where we have a biotin connected to an amine, and we can attach those as well. So here's an example of a single layer microparticle structure. So in this case, we're working with two different types of particles. One are green fluorescent biotin coated beads, and the other are non-fluorescent streptavidin coated beads. And so you can see the difference in these optical images that basically half of them are fluorescent and they're kind of in this checkerboard pattern. In an electron microscope image, we can actually see the difference in surface roughness between the streptavidin coating and the biotin coating. And so then we can do this not just in one plane, but we can build it up into a large three-dimensional structure. So this is an 8x8x7 two-component nanoparticle assembly. And with more than 440 building blocks, this is the most building blocks anyone has ever used for assembling a structure out of optical tweezers. So this is the biggest optical tweezer assembled structure that we know of. So we're excited about that. So one of the things you might notice from that previous image is that the positioning of the particles looked pretty good, but it wasn't perfect. And so one of the things we're interested in characterizing is the positional accuracy. And so we can do this directly from that scanning electron microscope image. So in this case, all of these particles are supposed to be in vertical columns that are kind of perfect columns, but in reality, they're shifted. And so one of the errors we can characterize is this horizontal error. So this is the horizontal shift in the particle coordinate relative to these yellow lines, which would be the ideal horizontal coordinates of all the particles. If we do that, and from this image, we calculate that mean absolute error, we get a positional accuracy of about 60 nanometers. We were interested in what experimental parameters affect that positional accuracy. And so to test that, we've done a lot of studies on these 2D grids, where we have a grid of particles and we know exactly where we are intending to place them, but then in reality, there's a little bit of error. So you can kind of see the deviation from the red X's sometimes from these particles. And we found that under optimal conditions for these 2D grids, we get about the same result, the 60 nanometer positional error. So I'll discuss a little bit about the different experimental parameters we've looked at to see what affects that error. One thing we were thinking might affect that positioning error for those 2D grids is the density of biotin molecules that we've coated on our substrate. So again, these are the coatings we use. They have these silane groups. So this is for attaching to glass. So basically these silane molecules will bind strongly to glass. There is this long peg chain, which is really just a spacer. So that's kind of this little black zigzag here is that peg chain. And then there's this biotin molecule, which I've illustrated by this kind of red cube here. And so you could imagine that if our coating on the surface was very sparse and we try to bring a particle down, it might not actually land next to a biological molecule that we want it to capture with. There might not be a biotin there to capture the streptavidin-coated bead. And so that might lead to positional error. What we ideally want is a uniform monolayer. On the other hand, if our concentration is too high, we might end up with clumping in solution, where these molecules actually start to clump together, and then that could kind of cause a messy surface, and that could potentially lead to positional error as well. So experimentally, what we found is that indeed, if our silane concentration is too low, we can get pretty large positional errors here. But over kind of a couple orders of magnitude of silane concentration, we can end up with good positional accuracies, again, getting close to that 60 nanometers. Another thing that I'm illustrating here is we have a bunch of different video calibration routines that we do to make sure we aren't accumulating a lot of error when we're moving our stage back and forth many hundreds of times. And indeed, that video calibration kind of gives us an extra 30 or 40 nanometers of accuracy. We didn't really observe any impact of this silane clumping, so maybe we would need to go higher, but we didn't see that. Another thing that we can measure is the effect on placement success rate. So again, if our silane concentration is very sparse, we might try to deposit a particle and it just won't stick. And so again, here that's happening 50% of the time. But as long as we have a good surface coating, we can get a 90% placement rate. We also looked at differences in molecular weight of these molecules. So the molecular weight really affects the length of this peg chain, this peg spacer chain. And we could imagine that perhaps if they were very long, that might cause, again, kind of some messy binding where you have these tethers that are pulling the particle in different directions. But we didn't notice a very big distinction between different molecular weights of those chains here. So the last thing that also affects positional accuracy is laser power. So we're using this laser to create an optical trap. And if the laser becomes too weak, because we've turned down the power of the laser, then it's not trapping the particle tightly enough, and it's going to be moving around due to Brownian motion, and that can also lead to positional error. But we're working at high enough powers that again, we aren't seeing a whole lot of motion in the trap. So if we want to scale this to even more particles, so currently we're doing more than 400 particles, but let's say we want to do thousands or tens of thousands of particles. Eventually, we're going to be limited by how quickly can we go grab a particle and bring it back to where we want to attach it. So we've studied in depth how quickly can we move different types of particles. So what we do is we grab a particle, we accelerate it up to some constant speed, and then we hold it at that fixed speed, and then we decelerate that particle. And what can happen is if we try to move the particle too fast, the drag force from the water is going to end up just displacing the particle out of the trap, and the trap won't be strong enough to overcome that drag force. And so really we're looking for the place in which our gradient force from our laser beam is balanced by our drag force from the water. And what we find is that maximum trapping speed is linearly proportional to laser power at low powers. So again, we try to drag the particle faster and faster and faster until we found the fastest speed at which we can keep it in the trap. And we're going to plot that for different trap powers, different sizes of particles, in this case, different materials of particles, and there's basically a linear relationship. And so that agrees well with that theory that I showed on the previous page. I'll note that we can, work from microscale dielectric particles. So this is, 5 microns to about half a micron. And then we can also work with these metallic nanoparticles. So this is 100 nanometer diameter nanoparticles. So we were looking at trying to compare these experimental results to theoretical predictions of how strong should that trapping force be on those metallic nanoparticles. And so we went back and looked at this paper. This was one of the first papers where people had optically trapped nanoparticles, metallic nanoparticles. And the trapping force depends on this polarizability. So alpha is the polarizability of the particle. This equation is known as the Clausius-Mazzotti relation. And this paper basically claimed that equation 1 is valid when the skin depth obeys skin depth much greater than the radius of the particle. So these are made out of metals, so that means that the optical radiation doesn't penetrate very far into the metal, and so that skin depth is a measure of how deeply it penetrates before it's reflected or absorbed. And so for things like gold and silver, that's typically about 20 to 30 nanometers of skin depth. And so they are arguing that if your particle is bigger than 20 or 30 nanometers in radius, then this equation doesn't really work, and you have to use this correction. So we went ahead and looked at that, but we found that in the end that this is not actually a very accurate model, even though many people have been using it for those decades since then. So again, this is this Clausius-Mezzotti equation. The idea is you have nanoparticles that have a skin depth. So if your nanoparticle is maybe very small, the field can completely penetrate the nanoparticle. Whereas if it's very large, you're only going to get the electric field penetrating the skin or the outer layer of the nanoparticle. And so what they proposed is that when we're using the volume in this Clausius-Mezzotti equation, we should really only use the volume of the whole skin rather than the volume of the whole particle. And so this is a correction factor that really just looks at the volume of that skin. But again, as I kind of hinted at, what we found is that when we use those skin depth models, our error is actually much greater compared to more accurate models than when we do not use that skin depth. So here what we're looking at is we're looking at really just the light scattering, which also has to do with polarizability. And we're comparing a bunch of different models. We have me scattering here. So me scattering, we expect to be completely accurate in this case. So there's no real cause for me scattering to be wrong. And so we're using that as our gold standard. There's the basic Clausius-Mezzotti relation. There's also a radiation reaction correction that we can apply to that. And those are these green and yellow lines. And then when we use a skin depth, that's the purple and blue. And so again, we're looking at basically the error with respect to the me scattering, and that skin depth correction leads to 10% to 100% error, whereas the more simple equation, that Clausius-Mezzotti equation, actually provides lower error throughout the range in which a dipole approximation is valid. Once your particle gets too big, basically all of these models, except for me scattering, break down. We looked at the same thing in dealing with the forces in optical tweezers. So the previous slide was light scattering, and this is really forces in optical tweezers. And again, we find the same thing, but basically the error in the optical tweezer force is much greater with a skin depth correction factor, again, up to about lambda over 10. So we're using lambda equals 1064, than it is if we're using the Clausius-Mezzotti or Clausius-Mezzotti with radiation reaction. There isn't a whole lot of difference between those two models in this case. And this also agreed with some experimental findings from previous studies that had found kind of deviations between what was predicted with that effective skin depth and what the experimental results from other groups found. Okay, so let's go back to what I was talking about, which was we're trying to move these particles as fast as we can so that we can build structures as fast as we can. So that's what we're looking for. So what we can do is we can keep turning up our laser power beyond a linear regime. So what I showed you maybe about 5 slides ago was just the bottom left part of this plot, where all these lines are essentially linear. Basically, all these points fall on the line. But if we start turning up the laser power higher and higher and higher, eventually we reach a stage where that linear relationship breaks down. And for microparticles, we think we have technological limitations. So basically our stage starts vibrating if we try to move it too fast. And we can kind of hear those vibrations as well. And we think that's kicking things out of the trap. But for nanoparticles, we think we're actually running into a thermal limit. And we see our stable trapping disappears at power levels in this 150 to 250 milliwatt range, depending on the different material of particle that we're using. And we think this is due to kind of thermal effects and heat absorption. I'll talk a little bit about that on the next 2 slides. So if you think of particle heating, what could happen? You're firing this very powerful laser, you focused it down to a small spot right on your particle. You could potentially melt your particle, or you could potentially vaporize some of the water if your particle reaches kind of the boiling point of water. So if we want to model the temperature change of the particle relative to room temperature, that depends on the rate of laser heat absorption, the heat transfer coefficient. So you can think of this as the rate at which the particle is going to cool to the ambient, and then the size of the particle. So if we plug in different numbers, there's a fluid mechanics number, heat transfer number here that's called the Peclet number that basically relates the magnitude of advective heat transfer. So that's kind of cooling due to fluid flow versus conductive heat transfer, which is just cooling due to heat conduction. And what we find is that for our system, So this depends again on particle size, the speed at which we're moving the particle, the density of the liquid, the heat capacity of the liquid, and the thermal conductivity of the liquid. Our Peclet number is much less than 1, and so that means that conductive heat transfer is dominant, which is a little bit surprising because we're moving an object really fast, and so it's kind of like if you stick your hand out the window of a car, it feels cold because the wind is cooling your hand if you're driving fast. But even when we're moving the particle as fast as we can, the heat dissipation is still dominated by conduction. So your hand would feel just as cold if you're stationary versus if you're moving. So that was a little bit surprising, but interesting. And with this model, we predict kind of particle temperature rises on the order of a few tens of degrees. If we're going to heat this, reach this water vaporization temperature, we'd kind of need about 100 degrees, or maybe not 100. I guess you need to get from 75 degrees change. So we're not quite there. We're in the right order of magnitude, but we aren't modeling surface roughness, which can lead to hotter hot spots. And so we think we're kind of forming some of these like micro bubbles or nano bubbles on surface imperfections on these nanoparticles. And that's why we're losing trapping stability at those powers. So what we can do is we can then kind of create some predictive plots of what we think the stable trapping region is for different size particles. So this would be an example for gold and polystyrene. So the idea is we need a trap that's stronger than Brownian motion, and that's really illustrated by the region above this white dotted line. And then we also need a trap that's not going to be lead to water vaporization. We need to not heat the particle up too much. And so the idea is there's this little window between these two lines where we can achieve a stable trap. And then for polystyrene, we can get another window there. And I think I've said all of this stuff here on a previous slide too. So if we look at these final speeds, so we can achieve speeds depending on the particle size and material in this range of about 160 to 220 microns per second. And compared to speeds in the previous literature, this is one of the fastest. We found one example where they were going a bit faster, but that was with large particles. And again, this was almost a side note. This is not really the main focus of this article. The rest of these studies, the main focus of the article was looking at how fast can you move particles. And so we really tried to push this as far as we can. For a point of comparison, we can compare it to the Nanoscribe 2-photon polymerization system. They have kind of two ways of doing scanning. One is a piezo scanner, which is kind of similar to what we're using. We're using a piezo scanner as well. And we get similar sort of speeds there. They also have a galvanometric scanner, which can go much faster. And so that's many orders of magnitude faster than what we can do. Again, it's a little bit different because in their case, they're continuously writing features, whereas we have to go grab a particle and bring it back. But this gives you kind of an idea of that size comparison. So we're still probably a little bit slower overall than 2-photon polymerization. But one of the main things we want to aim for is trying to get these smaller feature sizes and the ability to integrate different types of materials into the same structure. And we should be able to do that. So that's kind of an overview of this OPAL process and some of the performance specs and some of the studies we've looked at in the performance specs. I'm now going to focus on a couple of the device design and applications we've started to look at. So again, I listed a bunch of those early on in the motivation, but the two we're going to look at really are these microtoroid optical resonators that we've done some work with. But I'm going to talk a little bit about using nanoshells as transmission lines, and the rest I don't really have time to do. So this is a collaboration with Judith Su's group, and her group focuses a lot on using microtoroids for optical, biological, and chemical sensing. And so you could imagine this as being basically, it's a glass donut almost. So the idea is this glass rim, this toroidal shape here, is made out of silica, and it has an optical resonance where you could imagine light is going to travel around this in a circle. And when that light travels around in a circle, it's kind of like light traveling inside of a waveguide, except the optical mode gets pushed out to the edge of that waveguide. And so you can imagine the optical mode is getting pushed out to the outer circumference of this microtoroid. So what happens is when there are some sort of analyte molecules, so this could be a biological molecule or some sort of other chemical molecule, if those get within the evanescent field, basically this kind of blue and green region that's just outside the glass, they're actually going to interact with the light. And when that interacts with the light, it changes the resonance condition of this resonator. And that resonance that was initially kind of a dip in transmission is going to shift. So the signal strength, how much of a shift happens, depends on the volume of these analyte molecules that bind. It depends on the electric field distribution. It depends on the polarizability of those molecules, that alpha in there. So there are a few different things in there. Detecting small objects, such as individual molecules, requires very narrow resonances, which is the same as a high quality factor for this resonance. Very precise peak localization. So if you could track this peak very precisely, that helps as well. And or large interaction between the analyte and the optical mode. So basically the brighter the light is where that molecule is landing, the more things are going to show. So one of the areas that we've been working on in this collaboration is try to improve the way in which light is coupled in and out of these resonators. So the most common way that the coupling is done is via evanescent coupling with tapered optical fibers. And so there's an example here. So the light would come down this tapered optical fiber. It would evanescently couple into the toroid. This is a top view of the toroid. The light would circle around, and then you have a photodetector on the other side measuring the output. The difficult aspect of these tapered optical fibers is that they're very thin, they're very fragile, and precise alignment has to be maintained throughout the experiment. They are, however, compatible with microtoroids. So grating-based couplers, we think, can solve these problems. So what we're wanting to do is we're wanting to use this OPAL approach to attach basically grating couplers directly to the side of this microtoroid. And we think they're going to be robust and vibration insensitive because they're directly attached. We can fabricate them again using OPAL. We think we can then achieve the coupling via low-cost optics. And the grating can be designed to maintain high Q and select a particular mode. And so this is a way in which we think we can make these devices more friendly for field portable implementation. So the first step is actually designing this, which requires accurate simulation, and that's still a challenge. So the challenge in these simulation approaches is really that the toroid is pretty large compared to the wavelength. So there's a lot of volume to simulate in 3D. 2D simulations aren't really super accurate for these three-dimensional toroids. Smaller toroids could be simulated, but again, we'd really like to simulate the full real device that we're working with. Previously, one group published a study on using a small wedge of the three-dimensional resonator. It could be a toroid or a sphere or something like that, and just simulating this wedge with mirror boundary conditions. But the problem with mirror boundary conditions is that you end up with a standing wave, no matter what you do. And so there's no way to get these kind of traveling waves that are in a lot of cases what we see in these microtoroids. So what we've done is we've developed a new set of boundary conditions to basically handle this. And so we call these this Floquet wedge boundary conditions. And we've coupled that with a beam envelope method. So the boundary conditions correctly handle how the polarization is being rotated as it leaves one side of the wedge and coming in at a different angle on the other side of the wedge. And that's this kind of polarization rotation matrix here. And then the boundary conditions also handle the idea that if light leaves one side, it has to travel all the way around the toroid. And when it does that, it accumulates phase and loss. And that's governed by this parameter gamma here. And so the total amount of arc length that's covered by that rest of the wedge is 2 pi minus the wedge angle. And then this is the phase and loss. And so we can very accurately model this system with these kind of more advanced boundary conditions. So with these results, what we can do is we can simulate coupling light in from the far field into these antenna arrays. We can verify that we really are able to maintain a high quality factor. And so our quality factor drops about an order of magnitude, but it still stays up at about 1 million with these gratings. There's good agreement in the quality factor between different types of simulations that we do, these eigenfrequency and frequency domain simulations. In the driven system, so in this case, we're kind of looking at the light that comes in, hits our toroid, and then gets scattered back out again. We see these Fano line shapes, which is what we'd expect to see. And we're really tracking basically these small little resonances that, although this looks pretty small, it's still significant enough relative to the background that we could lock onto it and track that. And as I said before, we can recover these traveling modes. We can also recover standing wave modes depending on how we tune our boundary conditions. So the traveling wave mode, we expect to see a uniform intensity of the mode through our device if we just look at the magnitude of the electric field. Whereas if we had a standing wave mode, we would see these nodes and antinodes in our magnitude of electric field. And so we started to do this. So these are preliminary results that were just basically we got a couple days ago. So we're still kind of working on this, and we have some exciting results. But here is preliminary results positioning these 1 micron spheres on the edge of a microtoroid. And so here you can see we're starting to kind of build up a grading, and we're really working towards making this smaller with smaller particles, closer spacing. So another application that I said we were going to look at are these nanoshells, which we're using as building blocks for transmission lines. So these building blocks are gold on the outside and 112 nanometers in diameter, and then a 78 nanometer silica core. And they should work very well in theory for creating these transmission lines. What we do is we buy these commercially, but these are particles that we need to attach the biotin and streptavidin ourselves. And so we can do this by monitoring the shift in their plasmon resonance as we attach biotin and streptavidin. And so we can see that as we make this molecular attachment to change the surface coatings, these resonances shift slightly. So this is a kind of a simulation of a structure we've built. We're using these europium chelate particles as fluorescent emitters, and we're hoping that this fluorescent emission is going to be guided along this chain. And we're really working on trying to kind of scale this up to a larger number of particles at this point. This is an example of kind of where we are right now. So again, we think there are about 5 particles attached to this europium chelate, but because everything is so small in this system, it's really beyond the diffraction limit of a normal optical microscope. This would be a bare europium chelate particle, and this is a europium chelate particle with those nanoparticles attached. And so if you kind of compare these two as we scan through focus, you can kind of see that gold trail coming up and to the left a little bit. So we think we've attached them in 3 dimensions, and we still need to make this a little bit longer to get conclusive results in fluorescence. So one of the main simulation approaches, which I showed you on the previous slide, is this coupled dipole simulation method. And again, the idea is we treat each of our building blocks like a dipole, and we work out how does the scattered and emitted light from all these different dipoles interact with each other and couple with each other to result in the overall electromagnetic field throughout the whole system. And so this coupled dipole method we think is pretty powerful. It gives us full vectorial near and far fields, and it's really like solving a big system of simultaneous linear equations. And one of the main reasons why we're excited about using this, especially for designing more structures going into the future, is that we found that it's much faster than finite difference time domain, which is what a lot of people kind of turn to first in nanophotonics, is these finite difference time domain simulations. And so here you can see that the coupled dipole method is like several orders of magnitude faster in terms of simulation time than these different FDTD schemes. You can kind of tweak the accuracy of the FDTD to either make it be less accurate, which are these triangles, but run faster, or more accurate and run slower, like these circles. But that coupled dipole method is quite fast. And so we've been playing around with using it to design structures. So this would be like designing another grading type structure where we want to couple light from a waveguide to free space. And here we've kind of put this in some iterative optimization loop where we drop a particle down and let that particle kind of explore where is the best location in order to optimize some cost function. And so you can kind of see that over time, this begins to get closer to a gradient. One of the tricky things with the coupled dipole method is how to handle the effect of a substrate. And this is a paper that's in preparation. We should be submitting within a couple of weeks. We've kind of compared various approaches of handling the substrate, and we found one that's very accurate. So again, we're comparing our coupled dipole method, which is also called discrete dipole approximation. So DDA is the same thing as coupled dipole method. And we get very good agreement with our approach. And it's, again, much faster than FDTD looking at the situation. Okay, so in the short amount of time that's remaining, maybe 10 or 15 minutes, I will talk about how some of our work using lens-free holographic microscopes to build biosensors. So this is a little bit different than the OPAL that I talked about before. So the main overview of what I'm going to talk about in this section is we're trying to build a biological sensor. So we're trying to sense specific molecules, and in particular protein molecules. So of course, things like COVID sensors, if you're doing an antibody sensor or an antigen test, those are sensing proteins related to the virus. There's also a PCR test, which was kind of those first tests. Those are sensing RNA or DNA, these sorts of things. But if we're trying to sense proteins, that's really what we're trying to build here. So you can think of this as an easy to perform, rapid, and we're trying to get an accurate biosensor. But it can be applied to a lot of different types of diseases. So the general idea is we mix our analyte that we're trying to sense for with some beads that have been coated with capture agents for that analyte. And so those capture agents could be antibodies. We're also going to test this with our biotin-avidin system. Neutravidin is just kind of a different type of avidin. After we mix that system, we're going to flow it into a microfluidic chip. We're going to put our microfluidic chip on top of an image sensor, and we're going to capture these holographic microscope images, and then we're going to see if we can detect samples at different concentrations. So in this case, we're trying to sense interferon-gamma as a molecule. So ultimately, we want to develop a cost-effective, field-portable, sensitive, quantitative, and easy-to-use sensor for protein biomarkers. And the motivation here is to fill a niche between that of enzyme-linked immunosorbent assays, ELISAs, and lateral flow assays. So ELISAs are probably the most common biochemical method for sensing proteins. The idea is you have some capture antibody, you have the N-light you want to detect, you then have some detection antibodies here that cause a color change in some sort of dye. Basically, this enzyme causes a color change. And so if everything is kind of present in this change, you see that color change and you know that your target is there. Another very common kind of immunoassay is lateral flow assays. And so the most famous example there is a pregnancy test. And the idea here again is you deposit some sample on your absorbent pad. That's going to then flow through your system. It actually grabs little nanoparticles as it flows through, and those nanoparticles are again coated with antibodies. And those antibodies, if the target is there and the particles are there, they will bind to the test zone. If the target is not there, the particles will just bind to the control zone. And so that's why you see kind of 2 strips for not pregnant, 1 strip for pregnant. Or sorry, the other way, 1 stripe for not pregnant, 2 stripes. So what we're looking for is something that's more quantitative and repeatable than these lateral flow assays, but significantly less expensive in terms of hardware than ELISA and simpler procedures than ELISA. And we're also ultimately aiming for lower limits of detection and significantly faster response times. We aren't quite there yet, but we think we can get there. So our sensor approach is based on Lensfree optical microscopy. The idea here is the optical system is very simple. We have a light source, which is more or less like a point source. We have a transparent sample that we're wanting to image, and then we just have an image sensor. This would be the same sort of image sensor that you get from a cell phone or a webcam or something like that. The advantage of this is we get a very large field of view. So this area is much larger than you would get with a normal microscope objective of comparable resolution. It's very simple and portable, very inexpensive, but it's a little bit kind of intriguing. How do we actually form images? What is our resolution? What sensitivity do we achieve? So what we're actually recording on our image sensor is really this interference pattern between light that's coming through transparent regions of the sample and light that's being scattered off of the object. And so this interference pattern, you can think of an interference between a reference wave and then a scattered wave. And so that's exactly what a hologram is. A hologram is an interference between a reference wave and a scattered wave. And so these would be the types of images that we would expect to see on our image sensor. What we can then do is take that image and we can computationally reconstruct it using a backpropagation algorithm to form an in-focus image of our sample. And so all this is it's basically Fourier optics. We take a Fourier transform of our what we've imaged, we multiply by this transfer function, and then we take an inverse Fourier transform. So basically. And one of the advantages of this is that we can do this for a lot of different z distances, so we can refocus our image computationally. So most times when you capture an image, you can't change the focus after you've saved the image. In this case, we can kind of refocus and scan through a lot of different focal lengths. So one of the things that we want to do is we want to improve the resolution. Initially with this technique, our resolution would be limited by the size of the pixels on the image sensor. So a lot of times optical systems are limited by the numerical aperture of the lens. Here we don't have a lens, and so our initial limit is really the pixel size on the image sensor. So what we can do is we can capture multiple images of a sample as that sample essentially gets scanned back and forth across the image sensor. And so you can imagine if you look at the side, this is what's going on. Another alternative is we could shift the light source. And in this case, you could imagine the shadows are shifting back and forth across the image sensor. What we can do is we can use that to go from low resolution, kind of very pixelated holograms to higher resolution holograms. So once we have all these low resolution holograms, how do we do that? We can formulate this essentially as an optimization problem. So in the optimization problem, the idea is what is the kind of best fit high resolution image that agrees with all of our raw data? And we can either just kind of put all this into the model, or we can apply what's called a regularization parameter. And so this regularization parameter is basically something that tries to reduce noise in our system. And so we've explored a few different cases of how can we reduce the noise. One way of reducing the noise is we should say that there shouldn't be a whole lot of change from one pixel to its 4 nearest neighbors. And so if there is a lot of change between these pixels, we're going to penalize that, and that's going to help us kind of get less noisy images. So looking at how this operates, if we have a raw hologram and we just reconstruct a single frame, we see this. So this is a typical resolution test target. What I'm going to do on the next row is zoom into this region here. So this is this group 8 set of lines. The line width for group 8 element 3 here is about 1.5 microns. The pixel size that we're using in this case is 1.25 microns. So this is pretty close to the pixel size. And really, this is probably the resolution limit from a single frame. Once we do that pixel super resolution, where we've kind of combined all these frames together, we can really see group 8 element 1. And then if we do a little bit of this cardinal neighbor regularization, we can see probably still group 8 element 1, although it's a little bit smoother. I think a lot of people would say this image is a little bit better than that image. So here we're really getting sub-pixel resolution out of this. We've also looked at other regularization approaches in order to try to sense small targets. So if we have more knowledge about the type of sample we're wanting to sense, so in this case, we know we're looking for like individual particles or individual beads. What we can do is we can say, given that prior information about our sample, what's a way of kind of reducing the noise or increasing our signal to noise? So this is our average peak signal to noise ratio, APSNR. And if we do this sparsity promoting regularization, we can actually get higher average peak signal to noise by about 8 decibels using this approach. So we've kind of looked at, depending on the feature size and how densely covered our surfaces, what's the best regularization to use. So if you have a sparse sample, we want to use our sparsity promoting regularization, and there are 2 different kind of weights that kind of work well depending on the feature size. If we have a more densely packed sample, that cardinal neighbor regularization works a bit better. We're also working on further improvements in reconstruction accuracy by trying to also move away from this angular spectrum reconstruction approach, which is what we've been using so far, and try to apply coupled dipole method approaches. And the reason here is that the angular spectrum method is not really very clear on what the best way to model the interaction of light and matter is. So how do these nanoparticles change the light as the light passes through it? So the kind of naive way to deal with this would be an optical path length argument. And so this is what people use for doing Fourier optics of lenses. But for nanoparticles, that optical path length argument doesn't really work very well. That's these red dots here. And again, we're getting kind of more than 100% error in what we're seeing. Whereas there's some other approaches that work a little bit better, again, for very sparse arrangements of particles. We can kind of use a different transmission function here, and we can get less than 10% error for ways. But again, once our particles start to become densely packed, we really think this angular spectrum approach is breaking down, and we're kind of excited about applying these other approaches to try to further improve reconstruction accuracy and resolution to these small targets. So we're going back to this biosensor. So what we're trying to do is we're trying to sense these beads that are in solution that are functionalized with antibodies for a particular target. And so because they're in solution, they're really bouncing around quickly due to Brownian motion. And so if we want to do that super resolution approach, we need to acquire our images really quickly. And so we've developed our own custom LED array that's going to very quickly flash on different LEDs at different positions. And it's going to then illuminate the sample from slightly different angles. And it's going to allow us to get a full set of super resolution frames before our bead diffuses away too quickly. And so we've created a system to do that. So we've looked at the trade-off between the brightness and motion blur in this system. So again, if we switch our LEDs really fast, we don't actually get enough light, and that negatively impacts our signal to noise ratio. And then if we leave our LEDs on too long and we're switching them too slowly, we end up being kind of limited by motion blur. And so we've found this sweet spot. Again, these are looking at kind of different amounts of sedimentation time or the different configurations and different distances between the light source and the sample. But we found a region where we can recover that image with pretty good signal to noise, even for these beats that are kind of bouncing around fairly quickly. So again, what we're trying to do is we're trying to do clustering to sense what's going on. So to sense these targets. So what we do is we take beads that are coated with capture agents, and for Interferon-gamma, which is this protein molecule, we use antibodies. The other target we've sensed are free neutravidin molecules, and in that case, we're using biotins as our capture agents. We mix our analyte together with our beads. We flow it into this microfluidic device. We put the microfluidic device on top of the image sensor. We capture images like this, and we count the number of clusters. So if we see a whole bunch of clustered beads, that probably indicates that there was a lot of that target that was there that's kind of creating this sandwiching. And if we see a whole lot of beads that are just by themselves like this, that are monomers, then that means that that target isn't really there. And so we've developed a kind of an automated system for counting and sizing more than 10,000 beads. So because our field of view is very large and our resolution is very good, we can count a very large number of beads in one field. So here we're looking at counting the percent of beads that are bound. So that's that bound ratio as a function of different concentrations of our analyte that we're flowing in. And we kind of see this response here as our concentrations become higher. So this is the effect of neutravidin sensing. We've explored sensing a lot of different concentrations of neutravidin. We've also explored different concentrations of beads. So this is the number of beads that we're mixing with. And we get kind of different sensor response curves for all these different levels of concentrations. The binding curves exhibit a peak. So they come up and then they come down again. And the reason for that is that at very high concentrations, we could end up completely coating a bead, all the beads with neutravidin, before the beads have a chance to bind to each other. And so that's why they come down here at high concentrations. At lower bead concentrations, the peaks tend to shift to the left a little bit. The maximum bound ratio decreases a little bit, but advantageously, we get kind of a better limit of detection. So a lot of cases, what we want in these sensors is we want the most sensitive sensor. That means we want to see responses for really low concentrations of analytes. And basically, whatever sensor kind of gives us our best result, it's going to be the best sensor. So in this case, our limit of detection is somewhere below 30 nanograms per milliliter, which is clinically relevant for a lot of different types of diseases that are characterized by protein biomarkers. We also tested, again, interferon-gamma. So interferon-gamma, it's a molecule that's this family of cytokine molecules. It's an immune system biomarker. It's involved in many different types of infectious and inflammatory diseases, including COVID-19. So you might have heard on the news about one of the causes of death from COVID are these cytokine storms. Basically, your immune system becomes hyperactive due to a release of a lot of these type of biomarkers. So it's related to that. We've also been collaborating with a group that works on studying leukemia and the effects of graft versus host disease, which can result from bone marrow transplants for treating leukemia. And again, if the host is rejecting the bone marrow transplant, that can be predicted by an increase in these protein biomarker levels. So if we do that, we can produce these same sort of curves. This is a picture of what that interferon-gamma molecule looks like. And in this case, we get a little bit better limit of detection below about 3 nanograms per milliliter. So here we're using bovine serum albumin as a negative control to make sure that our sensor response really is specific to a particular type of protein that we're supposed to capture with an antibody, and it's not just sensing total protein concentration of all types of proteins. Okay, so I think I've run out of time, so I will end there. And these are the main conclusions. So with OPAL, we've kind of positioned the largest number of building blocks assembled to date using optical tweezers. We've demonstrated fastest nanoparticle building block manipulation speed. We've created an accurate model of trapping forces on nanoparticles. We have developed some new methods of designing and simulating kind of nanophotonic systems that we're going to build with OPAL. And we've developed a new biosensor method here based on Lensfree holographic microscopy for sensing protein biomarkers at relatively low concentrations with an approach that can be field portable, and we're going to be able to make it more rapid in the future too. So those are the main conclusions. So I would be happy to stop there and accept any questions at this time.
Thanks. Do we have any questions for Euan?
I do have a question. Miro Kolesik speaking.
Hi.
So I was surprised to hear that it is the speed, how fast you can transport building blocks, that sets your kind of limit to complexity. So if you could move these particles as fast as you wish, what would you build? And what would be the complexity and purpose of these structures that Yeah.
Right. So we think, so they're basically, you're right. There are a few different things that could limit the ultimate speed and complexity. One is how fast we can move objects. Another is how close can we place our microfluidic inlets to where we want to build. So that would reduce the distance, make things go faster. Another approach would be to multiplex using things like holographic optical tweezers to kind of deal with multiple of these in parallel. If you kind of put all of this together, we think the best you could really hope for is maybe about 1,000 building blocks per second. And that's kind of being pretty optimistic. We think probably we get to 10 building blocks per second. I think once we start to build that, this would be really useful for prototyping, for example, metamaterials would be one example, 3D metamaterials. So the idea is there are different designs people want to build, and they want to test it out in real life before they figure out a way to mass produce, many, cubic centimeters of it or whatever. And so we think of this as kind of like a rapid prototyping device. So it's kind of like applications where 3D printers have become useful, or it's where people are wanting to build and test one-off of something. Another area is this augmentation area. So things like the microtoroids, for example, we don't think that there's any other really good way of augmenting these complicated 3D structures that are lifted off of a substrate. And so that's one thing we can augment. We could also augment integrated photonic devices. So the idea is you make your integrated photonic chip, you cover it with lots of functional elements, but you just want a few things that you're going to add. Maybe it's going to be like a little bit of a gain medium that you put somewhere to make a laser, and you augment it so fairly small areas. So I think those are what we're looking for with increasing complexity, perhaps. I don't know. I think there are a lot of other ideas, but that's maybe a few ideas.
Do we have other questions?
Well, I have one more if there is space.
Yeah.
I see that you do a lot of computing related to this. What is the Maxwell solver which you use? Is it homegrown, or is it commercial software? What is it that you use?
We do a mix of a lot of different things. So for those microtoroid simulations, we're using COMSOL commercially. For the coupled dipole method, we've written our own solver for that. So we've written that, and we're running that in MATLAB, basically, that we wrote ourselves. For our FDTD validations, we use Lumerical and RSoft in a lot of cases. For kind of the reconstruction type stuff for lens-free holographic microscopy, that's done using MATLAB as well. So that's written using our own code. So I think those are basically what we use.
Do we have other questions for you? So are there any sort of limitations on what kind of materials you can incorporate into your structures?
Well, so right now, using the trap we have, it needs to be something that we can optically trap, is the answer. If you have very large metals, so if the metal particles are larger than about 200 nanometers, they can't be trapped using this kind of focused Gaussian beam trap. What you can do is you can try to create these optical bottles, so there are these bottle beams. But so right now we wouldn't be able to trap very large metallic particles. In general, particles, the largest particles people can trap is in the kind of tens of microns range. Once you get above 100 microns, it's kind of difficult to do any sort of optical trapping with that. So that's a limit. Another limit is the particles have to have basically they have to be more polarizable than the background medium. So that for dielectrics, that means like a higher refractive index in the background medium. And so we would need to be able to trap those. Again, there are other ways you could potentially change your beam to deal with that, but those are the limitations. So there's kind of a lot of flexibility. There are a few limitations, but there's a lot of flexibility.
Thank you. Do you have any other questions for Euan? So if not, we can switch to the meet and greet portion of the colloquium, which may not necessarily be so necessary given that we all know Euan. But does anyone want to ask Euan any questions in the meet and greet, which is designed to be a bit more informal, and the questions do not have to necessarily relate to his talk. I see Masood has turned on his video, so.
I had a question for Euan, but then you moved to the meet and greet part.
Oh, well, yeah, please ask it. We can go back. We can go back.
Have you done any measurement with the polarization of light to see if different polarization states can have more can be more effective in trapping the particles or moving them around, let's say circular polarization versus linear polarization?
We haven't done any experimental measurements on that. We've done, I guess we've done a few kind of simulations of what the spot looks like for different polarization. So one thing is for if you have a tightly focused beam that's linearly polarized going into the objective, then you're going to end up with like an elliptical spot, and so that's going to give you a stronger gradient in one direction. So really, you want to if you're going to try to translate at high speeds, you want that strong gradient, and so it's a little bit more efficient to go with if you're going to move horizontally, you want vertical polarization coming into your beam. So we've set up our system to do that in terms of polarization. We haven't looked so much at using either circular or radial or azimuthal, any of these type of polarizations going into the beam yet. But I think that would be interesting. It would be especially interesting for some of these potentially bottle beam traps if you want to trap, you know, larger metal particles or something like that. But we haven't done that yet. No.
So really, it's an open discussion at this point. So whoever wants to introduce themselves, ask a few questions. I know most of you guys probably already know you, and otherwise I can just start with my usual questions, such as what's the next big question you'd like to see someone else work on?
I have one more question.
Yes, please, yes.
Going back to what is it possible to build? If I understood correctly, you have these neighbors which like each other and neighbors which do not. So in some sense, is it fair to say that your structure has to be kind of like a, you know, two lattices that have to separate each other, you know?
Yes. So right now, if we want to
antiferromagnetic order, or you know, what is it that you can build?
Right. So there's no repulsion between the particles so much. So it's not like an electrostatic binding. It's like a protein. I mean, it's a little bit like an antibody binding to something else, this biotin-avidin interaction. So you can put two particles that are both coated with the same coating right next to each other. They aren't going to repel each other. But if you want like a strong mechanical stability, then yes, you need to make sure that you have like A binding to B, binding to A, binding to B, and so on. So as long as you can devise your structure that way, and there's nothing to stop it being the same type of building block. So you could have, if you want everything to be, 100 nanometer diameter gold, you could have half of those be coated with A and half of them coated with B. So you could make something out of a single material, but it's just got slightly different coatings. I guess one limitation is there's a little bit of a gap. So the size of these molecular coatings is about 5 nanometers, perhaps. So there's a little bit of a gap between your particles. So let's say if you wanted something to be electrically conductive, and you want to attach them, what you might have to do is a little bit of post-processing. So for post-processing, what we do now, we build it in liquid, and then we do a supercritical drying process in the clean room. So we take it to the clean room, we do supercritical drying. So we can bring it out of liquid. And what we could potentially do is sinter it to kind of weld everything together. If you put it in an oven at precise temperature for the precise amount of time. So we think that within those requirements, there's a lot of interesting things we can build. For a lot of these optical applications, it's not really necessary to have direct contact between the different types of elements.
Can you correct errors? You have shown the structure which, you clearly see that, some of the building blocks are maybe off. Can you go back and take it back and try again?
So right now, no. Right now it's permanent. Once it attaches, there are ways that we could try to play with how strong the binding is. So if we weren't going to use this biotin avidin binding, but we use something else that's maybe a little bit weaker, potentially you could find a situation where the force of the optical tweezer is enough to pull it off the system. We haven't really tried to do that, but that would be an interesting approach in the future, yes, to see if there are ways to correct errors there. Again, we haven't really looked at it because we're worried that the whole thing might fall apart if, like, someone bumps the table or something, right? If the binding is not very strong. So we tried to make things as strong as possible. Good questions, though. I appreciate the questions.
Anyone else?
When you try to move these particles through the solution, the friction forces are usually the thing that control the speed, that limit the speed. Is it possible to use some sort of surfactant to reduce the wettability of the particle or restriction of the water molecules to it so that you can move faster? Or could you possibly move it through alcohol or some other liquid instead of water to get to the maximum speed?
So the first, yeah, that's an interesting question. So the first question is can you use something like a surfactant? So probably that won't make a big difference. So a lot of times in fluid mechanics, there's this like no slip condition. So if you're modeling things flowing through fluid, the idea is that all the models start with the assumption that the fluid flow right at the surface of any solid object is 0. So there's no slip of the fluid around there. There have been a few studies that show there is a little bit of a slip. And so a lot of times it's measured in like slip length. And so usually that's on the order of a few nanometers of slip of how much that fails. So if you have kind of microscale beads, I think a surfactant wouldn't really help you, because what comes into that drag force is just the viscosity of the liquid and the size of the particle. There's no surface energy term. So a surfactant would lower the surface energy, but that doesn't come into that drag force unless you violate the no slip condition. And I don't think we're going to be violating that significantly in any case. But if you use different liquids, for sure, that would change things. So lower viscosity liquid is the main thing that can help you move faster. So if there are things that, like alcohol, for example, I don't know exactly what the viscosity of alcohol is, but there are things that with lower viscosity than water.
How about surface roughness of the particle itself? Like on the airplane wings, they create roughness so that they could create micro vortices and reduce the friction.
Yep.
That also be a way to speed up the motion.
Yes, I think you could if it's smoother. Again, I don't know. I'm not sure how much of an impact that would have on that. It's an interesting question, but yeah, I think it would. For sure, the other way that we think surface roughness affects it is if there's surface roughness on, say, like a plasmonic particle, you get these plasmonic hotspots at that surface roughness, and we think that can lead to higher temperatures and higher heating, which limits how much we can turn up our laser beam. And so we think surface roughness would play an important role there. So smoother particles there would be more helpful. But yeah, I'm not sure how much of an impact surface roughness would have on drag speed, on basically drag force.
I imagine that even if it's rough, the surface, it would be kind of laminar. Is it possible to have vortices on that very small scale? You would need a lot of energy to create them.
Yeah, the Reynolds number is definitely far below 1. So everything's pretty laminar. You can have things spin. For sure, people have had particles spin in optical traps using things like polarized light and birefringent particles, or using orbital angular momentum to cause things to spin. So in some sense, if that particle is moving in a circle, then there must be some fluid moving in a circle too, somehow. But I'm not sure exactly the details as to how much of an impact that would be. Good questions, though.
But given the theoretical understanding of the friction forces and viscosity and all that, are your particles moving at the fastest possible speed, or are you still below that that upper bound?
We're moving. I think we're moving pretty close to that fastest possible speed. I think we're not right at the edge because there's a chance we might lose it, and we want to make sure that we're not going to lose the particle. But we're for sure, you know, within kind of like a factor of 2 of that fastest up or down. So right now it's maybe about the speed that we're doing is about a minute per particle. So it's kind of slow. The first way in which we're going to speed that up is by kind of improving the automation in which we grab particles. Right now, the placement is fully automated, but the fishing for the particle at the beginning is not completely automated. And that's really what takes the most time right now. And then after that, it's going to be that translation distance. So if we can kind of shrink the translation distance, I think that's then the next step in how we're going to speed.
Is it the software that fishes for the particle, or is it human aided?
Right now, that part's human aided. So it's kind of semi-automatic. Once the particle is caught, everything else is automatic, but the fishing is done with the human right now. We have a quadrant photodiode that we're going to use as a feedback mechanism for that fishing approach, and it's not fully implemented yet, but we're working on that. But even with this semi-automated method, we've still been able to kind of create the largest structure anyone has created because it's pretty robust in terms of our kind of positional error correction on the fly.
So there is, you know, competition to build the biggest right now, because so at some point there will be the competition to build the most complicated, I guess.
Yeah.
Something. Yeah, interesting.
Yeah.
I think that's, does anyone have anything else?
Good.
Not, do you want to end on what is the best advice you have for graduate students, Euan?
The two graduate students left. No, one graduate student left. Jeffrey's graduated. I guess my advice, so I'll do this mostly for the recording. My advice is to
You have more deans than graduate students.
is to find an area that you're kind of passionate about and want to work on in graduate school pretty quickly. So don't spend like many years window shopping around to find the area you want to work in and the group you want to work in. So find enough time to kind of make a decision you're happy with, but don't kind of spend forever drifting around. I think that's my advice.
Okay, so I guess that's it. Thank you. Thank you everyone for being here. So
okay.
Thank you very much.
Thank you. Thank you very much for everyone who stuck with me to the bitter end. Okay. Thank you.
Bye.
All right.